Hello everyone, my name is Jen Li. I'm a software engineer from Microsoft, and today I would like to tell you about service house monitoring for Office 365 and how we build it on top of Spark streaming. In case you don't know what is Office 365, they are backend services that support Microsoft products such as Yammer, Skype, and Exchange. These services have millions of customers, and so service house monitoring is really crucial here. So in general, our approach is that we model data stream processing as temporal operators, and these operators are very similar to Azure Stream Analytics, which is the product team that I'm on. It's a hosted web service on Azure platform for data stream processing. So this work is a collaboration between our team and Office 365 Customer Fabric team. And Wesley Mao, my colleague, is actually from the Office 365 side. But today, due to family emergency, he cannot be here. So I will be doing the entire talk. So this is the system overview of the new monitoring system we are building right now. There is already a production system running, but due to various extensibility and scalability issues, we are building this new system on top of open source technologies. So you can see that on the left side, these are the target services that we'll be monitoring, and the raw signal will come into Kafka. Kafka is our data bus. And then most of the data processing happens in Spark streaming, and the result goes to Cassandra. And then from there, we can do a lot of interesting offline analysis and dashboarding. Two types of monitoring events comes from this Spark streaming processing tool. One type, we call it recovery actions. Recovery actions are actions that can be automated. For example, reboot a host, or replace a host, or add more hosts into a cluster. And then the second type, we call it alerts. Those are things that we need a human being to investigate. So for the rest of the talk, there will be two parts. First, I would like to walk you through the application logics, and then show you how we translate the application logic into temporal operators. And the second part, I would like to talk a little bit more about the operator implementations. So for all the applications, the most important thing is about the data. So first, what's the data like? What is the data into the system? We take a local active monitoring approach, which means that we generate a pin requests on each local box, and those pin requests will hit the service that locally running on the host. And then based on the response, we'll derive raw events. Monitoring events. And the schema of the events will be like topology scope value. Its success indicates if this is a successful pin request or not, and etc. And also, there is a timestamp of when this request happened. So topology value, scope value shows the grouping of hosts. Normally, it's a hierarchy. For example, server, rack, site, or data center, and then region. Because the data is generated in such a distributed way, we cannot guarantee that data will arrive in order when it gets to Kafka. Now, most often, it won't. There will be some certain delays. However, our monitoring application logic is defined on data time. So that's a challenge for us. And this is not a unique challenge just for service house monitoring. I believe in a lot of other applications, you see this too. For example, in IoT scenarios, right? You have a lot of sensors very distributed, and then when the sensor data hit your system, normally it won't be ordered also. So we believe this work should apply in general to a lot of other use case scenarios. So now let's go through the Spark processing pipeline. So a few steps here. First is normalization. And the raw event generated on each local box only have the server name, doesn't have the topology data such as which rack, which data center, which region it belongs to. So there is a data string and a static data join here. And after that, we will need to reorder the data. So reorder is the way we're dealing with out of order data arrival. We require that if you use this, our temporal operators, reorder operator must be the first reorder operator you use if you know your data will not be guaranteed to be ordered by application time. And then after that, we will use an aggregate operator to compute various basic metrics. For example, the average latency, the availability, and etc. And then we will derive monitoring events from those basic aggregates. So then here, this reorder operator takes a parameter, which is the reorder policy. For example, here, this reorder policy have two parameters. One is 60 seconds, the other one is 120 seconds. This means that for events that arrived late, but it's within 60 seconds, put it back in order. But for events that arrives late between 60 seconds and 120 seconds, adjust the application timestamp to the latest application timestamp we got so far. Beyond that, drop the data. So the setting of those two constant values have to be based on your application, because here we will buffer a certain amount of data in order to sort late tuples back in order. So you will have to trade off the amount of memory you would like to use for the reorder buffer versus what's the percentage of the data you are willing to drop. And then next is the aggregate operator. So here, the aggregate operator will take a window definition. In this example, we are using a tumbling window. Tumbling window are non-overlapping windows. So here we use a tumbling window of 5 minutes. And then you can specify grouping attributes. This is like a regular group of aggregates. And then followed by a list of aggregate functions. Here in this example, we want to compute availability. So we need the total number of success events versus the total number of events. So that's the first two things we're computing. And then we want the average latency too. So the aggregate operator will give us those 5-minute basic metrics for service house monitoring. And then when we generate monitoring events, the general rule is that when the system is under alarm, you don't want to generate duplicates. And so we model this processing as a self-join. So what we do is, sorry. Okay, so for the monitoring, we want to, so let's take availability as an example. If, let's say we want to capture scenarios where the system availability is below 99%. So, and then if we already have alarm that the availability is under the threshold, we want to dedupe for the monitoring events. So here's how we model it, right? So we model it as self-join, and then we specify the join key for the left and the right. They are both topology scope values. And then we will say on the left side, the availability is below the threshold, below 99%, and on the right side, the availability is greater than the threshold. So when you are not under alarm, when the system is healthy before, now you are in a bad state, generate alarm. Otherwise, if the system is already in a bad state and you are rediscovering that you are in bad state again, but don't generate the events. Oh, no. So next, I would like to talk about the temporal operators we used here in a little bit more detail. We talked the 3 temporal operators already: reorder, window event time, window aggregate, and the join. So these are all stateful operators. Across all the implementation of the 3 operators, we use update state by key because we started this project when the latest Spark version was 1.4, and later we moved it to 1.6. So first, the reorder. When we get the input, we always need to map it to string event type, which have 2 fields. The first one is the application time. The second one is the payload of the data. And then suppose we take a simpler example. Here we are going to do a reorder with reorder policy of 60 seconds, which means if the data is late by late within 60 seconds, sorted back in order, but beyond that, just drop the data. So let's say, suppose we already got events with timestamp 10 o'clock, 10 o'clock 1 second, and 10 o'clock 3 seconds. We maintain a high watermark timestamp, which is the largest timestamp we got so far. So right now, our high watermark timestamp is 10 o'clock and 3 seconds. And the next, suppose we get an event which have timestamp 10 o'clock and 2 seconds. This is a late arrival event, but it's within our 60-second delay boundary. So what are we going to do with it? We're going to sort it back in order. So we put it in the reorder buffer, and we don't need to update the high watermark timestamp now. This will be going on, and then until we got a new event with 10 o'clock, 1 minute and 1 second. What can we do with this event? In addition to put this event into the reorder buffer, we can actually output the event from the reorder buffer too. Why? Because we want to guarantee that the output from the reorder operator will be ordered on the application time. And when we get an event with timestamp 10 o'clock, 1 minute and 1 second, and our reorder policy is 60 seconds, we know that we will not output any tuples. We know that we can output all the events with timestamp smaller than 10 o'clock and 1 second. Right? Because for all the events that is late more than 60 seconds, we will for sure drop it. So we'll update the high watermark timestamp to with the new timestamp of the event. And then suppose we got a new event. This one has timestamp 9 o'clock, 59 minutes and 1 second. See, this is more than 60 seconds behind the high watermark timestamp. And so we cannot output it, and we don't put it in the reorder buffer. We'll just have to drop it. So after the reorder operator, only other operators can assume that the events are ordered on the application time. So let's next look at event time window aggregate operator. So here I highlighted different part of the input parameters for the aggregate operator. The red part is the window definition. The green part is the grouping attribute, and followed by the purple ones, which are the aggregate functions. So how do we implement that? This is the data structure we use to maintain state for the aggregate operator. So we use a hash table. Suppose now remember that we're doing a tumbling window aggregate of 5 minutes. Suppose right now we are incrementally computing result for the window 10 o'clock to 10:05, and suppose this is the state of the hash table right now. The key is the rack, and the values are the incremental sum and incremental count maintained for each rack. Then suppose we got a new event, which is for rack 1, which is a success event. That's what the last one indicates, and which timestamp 10 o'clock and 03 minutes. So we just use this one to update the rack 1's window aggregate. So both the sum and the count will be incremented by 1. And then this is the next event, also belongs to the current window, and it's for rack 2, but it's an unsuccessful event. So we'll update the internal state 2. And then let's say we got a new event for rack 2, which is a successful event, but the timestamp is outside of the boundary of the window. So remember that after the reorder operator, all the other operators can assume that it will get a ordered data stream. So once the window aggregate operator gets this event whose timestamp is beyond the window range, it knows that we can close the current window and on the state we can output. And then then we can start a new window. So I have a typo here. The window range should be from 10:05 to 10:10 to 10:10. So that's the window aggregate operator. And then the third one is join. The example here is self-join, but it's general enough to be applied on any data string join. So again, syntax-wise, we have you first specify the other data string you want to join, and then in the green part, that's the join key for the left side and the right side. And then the purple one is a regular joining condition, right? And then the last one, the time diff, represent the temporal constraint on the join. So for our join, you will have to have this temporal constraint. So in this example, our temporal constraint is for each event on the left, you will need to join it with an event with a range of events on the right. The range is the past 5 minutes. That's negative 300 seconds, right? And so in this particular application, because the input of the join is a 5-minute tumbling window. So each event on the left actually joins with a single event, which is the previous aggregation result, like 5 minutes ago. But in general, if this is a regular join of 2 events, one event may join in with multiple events on the other side. And the implementation of the join operator is that on each side, we will need to keep join state. The join state data structure is very similar to the the window grouping aggregate. And then the only tricky part is how do you purge the join state. If you don't purge, the state will just keep grow. So what we do is, for each event on the left side, it will help to purge event on the right side. For example, when you get the event with timestamp 10 o'clock on the left side, right? Because it will only be joining on the event for the past 5 minutes. So you know that on the events on the right side, that is before 9 o'clock and 55 minutes can be gone. So you can purge the state that way. And then, the system performance-wise, I don't have a slide for it, but the number is, for experiments we run with 20K events per second, with batch interval as a minute. The processing delay is about 20 seconds. So that's all. Thank you.
Well, thanks very much. So we do have a little bit of time for questions. So if you do have any questions, could you please come to the mics and ask away? And then that's about it, really, guys.
Yeah.
See?
And also, if you want to, you prefer to talk offline, so Microsoft has a booth this evening, so I will be there. You can come over and we can talk in person. I'll say it again, which slide? The first one.
Oh, yeah.
Is this one?
This one? Okay. All right, go.
Just wanted to keep that, look at that while she answers questions.
Oh, okay, sure. Okay. All right, go ahead, please.
Yeah, I was just wondering, is this open source by any chance?
We are talking about it. My personally would more than happy to do it.
Okay, thank you.
Any other questions? Just head to the mic, please.
Could you speak of the data collection agent that you put in place, the piece before the Kafka?
Oh, let's see. Do I have a slide here? It's a little bit. So it's the data collection part actually runs on the cluster that runs the Office 365 servers. So so they have collectors, right? What that does is a separated piece of code that will generate a pin request that will just hit the service running on that host. So this is called local active monitoring. So we actively send a pin request, and those pin requests happens locally. Does that answer your question?
Yes, I'm just also curious about, do you actually monitor, for example, application logs? But it sounds like you just basically ping just the services up or down, maybe some performance parameters, but deeper inside application log, whether the application logic is behaving correctly.
Yeah, that's true. So this mainly is for latency and availability. So there will be more. I hope Wesley is here because he's on the product team of Office 365 side. But my understanding is that so service house can be defined in multiple levels, right? On high level of availability, if the service can be reached or not, is the first level, and then we can talk about for different functionalities, is the function well or not.
Okay.
So this is the first layer.
So you're talking about emitting the data and purging out state when the window has finished, right?
Yes.
What does it mean to emit data? Do you have your write calls within your functions? What does it mean to emit? Do you emit as a D stream or?
Oh, that's a good question. So it is still a D stream, and it's a D stream of records we define. But with the data frame and the dataset APIs, we probably can make it even better. So the record is a key value pairs.